it's yours.
Thank you. First of all, I would like to thank Transvalor team for giving me an opportunity to present uh, the joint research project in this conference. Uh, the joint research project was on die wear prediction, which was done by ARAI team and Transvalor team. Uh, what is ARAI? It's Automotive Research Association of India, uh, which 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 is having the three units at Pune in India. Uh, we are we are actually giving services to many OEMs, component manufacturers, in the field of testing, homologation, and certifications. We also have training and academy for various industries and uh, various courses for the students. In the ARAI, I'm working in the EDS department. It's a engineering design and simulation service, and we do simulate and provide services in the various verticals, out of which you can see a manufacturing process is at here. Now let's move to our topic. The frequent shop floor problems in the forging process are fill up, fold slabs, tool die wear and tool breakage, tonnage under usage or over usage, grain flow prediction, trimming process issues, and heat treatment issues. Uh, out of which, the tool wear is one of the major issue on which study was carried out and will be demonstrated in further slides. Forging die need to be replaced after certain number of production cycles because of die failure, which occurs in any form, in abrasive wear, in thermal fatigue, mechanical fatigue, and plastic deformation. Out of which 70% failure takes place because of abrasive or adhesive wear. So our research work was to predict that before before going into the production cycle. So these are some of the critical parameters which are affecting the die wear. So these are some of the process parameters which we have identified, in which tool design, die material, process parameters like temperature, then friction and other workpiece material and other environmental and process conditions were also analyzed. Here, some of the significant parameters which can be quantified as highlighted here with their level of influences. So let's start. In the before predicting, we just need to take one component and uh, we have identified a critical component as a fork or a tube yoke, you can say. So that component was modeled in the CAD software, and we did its process simulation, and we have made a forging process for this component. We have also analyzed that most of the material is flown into the cavity without forging defects. The optimized die cavity design was given for die manufacturing. As you can see, a die was manufactured and suitable material was selected for component and the die inserts, which is widely used in the industries. We have used C45 or EN8 for component and H13 material for the dies. The forging process simulation was carried out for design components. You can see the animation for the blocker process and finisher process. As you can see, this is actually a video. We have produced 5,000 components on 250-ton mechanical press, which can be seen here. The sequence of the forged parts, the upsetting, then blocker and finisher component can be seen here. The forging dies, which is going to wear, that has to be physically measured. The die wear pattern has to be physically measured, and which we have measured in frequent number of cycles, forging cycles, with the help of 3D scanning equipment. So these scan results were compared with the original scan, means before going for the production, that was overlapped and matched for the difference. Here you can see a scanned die was overlapped, and we have taken the cross section of this, and this is the result for bottom die and for the top die. So the maximum wear regions were identified from the top and bottom die. So this is actually a video. Anyhow, you can see the wear pattern is at these regions here for the bottom, as well as for the top. Here is the maximum wear observed. So we have identified multiple locations on the die, in which 3 on the top and 3 on the bottom we have identified for the further study. So the graphs on these regions were plotted, and the animation shows how wear takes place at the different regions of the cavity with respect to number of cycles. Here you can see the number of cycles, means number of forgings were carried out, and how the wear is increasing on different regions. So this simulation, so this study, physically we have measured the wear, and now we need to correlate with the simulation software so that we can use that study for the other components. So in the literature, there are many wear models available, out of which few of them are listed in the slides. And among these wear models, three traditional, and one energy model was selected for the further study, as highlighted in the slide. Why I'm telling the traditional? Because these are the Archard models and further modified by other authors. Now, a traditional wear, first we will look to the traditional wear model. Here, the experimental forgings were done, its scanning was done, and the wear calculation was predicted. So this part of the study was already over. Now, the FEA simulation, in which the FEA analysis were done for the forging dies, in which steady and dynamic parameters were considered. Its simulation was done. Further, to predict the dies, die wear, we have used the experimental wear as an reference for predicting the further die wear on the in the simulation. Here you can see a loop to find the constants k. So these are some of the parameters which was used from the simulation results, and these are some of the k and VZ were analyzed using the regression analysis. So these three models were uh, more software coding was done in this simulation software, and further analysis was done. So let's see the Archard VM model result. Here the K constant, K abrasive is the constant, where also increasing with respect to the number of forging cycles. And with this K constant, with this K value, you could see a simulation result and the scanned wear value is having an error because of K is directly proportional to the wear. So we did one more iteration to fine tune the K constant, and you can see a K dash ABR is calculated, and with this the wear value is predicted. This is one traditional wear model. Now let's see the Felder Montagut wear model. Here one more parameter was added is the M arc, which is a constant, and we have considered 2 for the steel. Here the same K abrasive is also increasing with respect to the number of cycles, and here is the result in which a major difference you can see. So we have further modified and we have further iterated, and we got the K dash ABR, abrasive K factor, and you can see the difference between the scanned and the simulation wear was reduced. For Behrens, the formula is changed. The K Behrens is at the top. For sorry, M. So here also the K value is changing with respect to the number of cycles, and the value for wear is also having a difference between the scanned and the simulation wear. So we have further modified the K ABR, and we could able to achieve the some portion of the wear patterns. In this traditional, we cannot find we have not used the number of cycles. We cannot predict the number of cycles, but in the one more model, that energy wear model, in which number of cycles were considered for the calculations to predict the wear pattern after nth number of cycles. So this is the wear formulas for the energy wear, in which material property itself is considered for the calculation purpose with by considering pressure and sliding velocity and temperature into it. So this ratio gamma is yield shear stress to the friction shear stress is a factor to predict the die wear start after nth number of cycles. So the energy wear model mostly depends on the die material property along with few process parameters. So the ratio of yield shear stress and the friction shear stress helps to find the number of cycles at which the wear start. So this data further helps to find the wear value after number of forging cycles. So the energy wear model is the design of hot forging process that was already we have designed. It's further we have set the target of tool as n cycles, and then we have simulated. With this we have identified the friction shear and cumulative friction work to remove out the material from the die, which is called a wear, and the calculation of yield shear stress was further used to calculate the NC and W means wear. So this whole process or the whole square section was simulated in the software in a single iteration. So if you see the wear result in a single click or in a single iteration, we could able to achieve as per the scanned wear results. We have also here you can see A, B and C are the constants which are easily calculated using material properties and other simulation results. So with this production of 5,000 components were carried out and the die scanning activity was conducted at intermediate number of cycles. So abrasive wear pattern can be seen on the blocker and finisher dies on the forging dies. So the parameters derived from simulation results were used as an input for calculating the constants K, A, B and C in the different wear models. So the software coding were modeled and incorporated in the forged softwares in 2.0 and 3.0. The simulation results and physical wear results were compared for the traditional as well as the energy wear models. So the energy model gives a closer result with a single simulation iteration compared with the other wear models. And with the energy model, we can predict the die wear at nth number of cycles compared with the other wear models. Thank you.